Simulations gain more and more significance and, at the same time, more and more data becomes available. The Cluster of Excellence, Data Integrated Simulation Science at the University Stuttgart combines both of these areas and has defined 3 visions. Engineered Geosystems, next-generation virtual materials design and the digital human model.
My group, Simulation of Large Systems, provides algorithms, mathematical methods and software to solve the huge systems of equations involved in today's simulations. The size of these systems requires the use of supercomputers with a power consumption of several megawatt, which corresponds to the energy requirement of a small town. Our work can significantly contribute to use this huge amount of energy much more efficiently, that is, produce more insight per watt-hour. To give one example for such a challenging system, in the SFB 1313 we simulate the interaction between free flow and porous media flow. This is very important if we want to analyze evaporation in soil or the opening of fractures in porous underground structures.
The resulting systems of equations are very hard to solve. The state of the art is to use so-called direct solvers. These direct solvers are very robust, but are also computationally expensive.
For such a direct solver, our runtime increases dramatically if we want to increase the accuracy. Let's, for example, assume that we have a program that can solve a simulation problem in a cubic domain with 100 data points in every direction in a total runtime of 2 minutes. If this program uses a direct solver and we want to increase accuracy by increasing the number of data points per direction to 1,000, this would mean that our runtime increases by a factor of 1,000 cube. This results in a total runtime of approximately 4,000 years, which is clearly beyond anything we would like to wait for.
This means instead of a factor of 1,000 cubed, you would only have a factor of 1,000, which decreases the overall runtime by a lot. This means we could solve then in the end the same problem as before in just 1.5 days in total.
In the best case, we can achieve completely new results. With partners from Austin, Houston and Pennsylvania, we've developed a framework to identify the initial localization of brain tumors and growth parameters. We can do so based on just a single MRI image of a patient brain and within a few seconds. This contributes to improved personalized diagnosis and therapy. In this brain tumor project, but also in many other projects, such as a project on muscle simulation, interdisciplinary cooperation is really very important. Only with this cooperation we can develop theoretical methods that are actually helpful in practice and also exploit synergies between different kinds of applications that require similar methods. In a team of researchers from Eindhoven, Munich and Stuttgart, we develop a software called Precise. Precise allows us to couple different independent pieces of software to one complex simulation environment.
With Precise, we support a wide range of applications, from blood flow in arteries to fraction opening in porous media to optimization of geothermal energy exploitation.
In the future, Simtex tries to exploit available data in a more systematic way. In my project, I use runtime and scalability data in simulations to identify optimal combinations of models, numerical methods and algorithms. We are looking forward to tackle these challenges in the framework of Simtex.